Good morning. Today we're going to be taking a look at Chapter 3, Projectile Motion. And remember, projectile motion is motion in two dimensions, whereas earlier in Chapter 2 we were taking a look at just one-dimensional motion, either moving the x or in the y. Projectile motion is x and y concurrently. So here Megan is kicking a soccer ball, it's moving in the x and it's moving in the y direction at the same time. This is a pretty bad drawing. I doubt it's a parabola. It might be, but I doubt it. This is showing you that the flight of the ball is both x and y component. Let me move to full screen. Hopefully this will work a little better. Again, all of this content is review, so you have notes on all this from last year with Mr. Horrigan, and if you have any questions, just come see me. We'll do a practice set later in class. Remember, one of the most interesting aspects of projectile motion is that the motion in the x and y directions are independent of each other, which is kind of interesting. Remember, the typical problem we give you is asking about if I drop a bullet from a certain height and shoot a bullet horizontally at the same time from the same elevation, which one will hit the ground first? Most students have trouble with that. It's very non-intuitive. They battle back and forth, and through a couple different techniques you can arrive at the conclusion that they will hit the ground at the same time. I think you guys saw Mythbusters last year where you saw this happening. So again, the bullet will drop a certain distance, strike the ground, the bullet will be shot, fall the same horizontal distance. The motion in the x direction has no influence at all on the time to fall, which is again interesting and counterintuitive. I have a tutorial in a program called Interactive Physics. It's a program I'm not sure if you used last year. We may use it a little bit this year. It runs simulations, real-time simulations, to show, at least theoretically, what will happen. Here we have a blue sphere and a purple sphere. The blue sphere is going to be dropped vertically. The purple sphere is going to be shot horizontally with some x velocity component. Here I've set it arbitrarily to 12. When I fire this, you'll see they strike the ground at the exact same time. We can actually change the x velocity of this. I can increase the x velocity, and although it may have a greater range, again it strikes the ground at the same time. You notice that sound effect was interesting. So again, the independence of the x and y is interesting and real, and we'll take a look at why that's the case in just a second. The good news about projectile motion is that the kinematic equations, the same ones we use for one-dimensional motion, we're going to use in two-dimension. And you may recall we set up a grid to do this. We keep the x and y separate, but we use the same equations that we've learned before. This should be obviously an easy question. Two spheres are placed at height h. The red ball is dropped and the yellow ball is shot horizontally, which will strike the ground first. If you're having trouble with this, you might want to go back and watch the video again. But obviously it's going to be identical. The reason behind this, and it's kind of interesting that Mr. Horrigan and I teach this, we teach the laws first before we go into projectile motion. We think it makes sense to understand why. A lot of books will go Chapter 2, one dimension, Chapter 3, two dimensions, and there's really no explanation why. It really boils down, like most things, to Newton's laws. And the first law, and again this is review, deals with forces that are balanced on an object. So equal and opposite forces. If the forces are balanced, the ball or the object's going to keep on doing what it's doing. Same velocity, same direction. So objects keep doing what they're doing exactly. For example, I place a ball on the table, it just sits there. Forces are balanced, it just sits there. Newton's second law deals with forces that are unbalanced, when the forces are not equal and opposite, or there's a net force, something equal to a non-zero value. In that case, the object will accelerate. And again, a classic example is a ball that drops due to gravity, constant force. I always have a cameo. Here's a picture of an unknown person back in his college days. If you think back to projectiles now, which of Newton's laws best explains the motion of the ball in the y direction? First law, second law, third law, fourth law. There is no fourth law, so that's a giveaway. And none of the above, that can't be that. So, see, in the y direction, there's gravity, so I think it will be the second law. Which of the following best describes the motion of the balls in the x direction? Well, again, in the x direction, once the ball is projected, pushed, but we're talking about once it's in motion, it should be the first law. There's no balance force acting on it. Again, review. I'm probably going to go through this really quickly. This is a horizontal problem. I'm playing with this new tablet. I'm trying to learn how to use this thing, so bear with me. And apparently I can't even get it working anyway. This is a problem to work on kinematics. So a car starts from rest, VI is 0, A is 5. It does this for 10 seconds. Then we ask some questions. And I'm just trying something new, so bear with me. I have to go back in here, and I'm going to try to do this with my pen. Hopefully I didn't block out stuff. This is Khan Academy-esque, but poor man's version. Car starts from rest. So again, as any problem we've always done, we're going to say we're going to write down our givens. The V initial is 0, accelerates at a rate of 5 meters per second squared. So 5. It's going to tell you that happens for 10 seconds. So my time is 10. And they want to know how fast. So how fast is the car moving after 10 seconds? That sounds like VF to me. And again, the whole process here is write our givens, figure out what we're trying to solve for, think of the kinematic equations. This obviously looks like equation number 1, VF equals VI plus AT. We're going to use SNA like we always do. AP is big on partial credit. That's another reason why we SNA'd in Physics 1. VI 0, so that goes out. A is going to be 5. T is 10. And our answer is going to be 50 meters per second. Come on, pen. 50 meters per second. And we will make sure we have units, and we'll circle or box our answer, and we're fine. There are more parts of this question. I'm not going to go through them because I've probably chopped up the screen anyway. How far did the car travel during that time? Again, you can apply the kinematics and solve for that. You can go ahead and do that if you'd like to. Likewise, I have that was a purely horizontal problem. Here's a purely vertical problem at the prom. Please don't do this. A water balloon with a mass of 1 kilogram is dropped from the height of 50 meters onto the unsuspecting teachers below. How much time does it take for the balloon to strike the ground below? Again, same thing. We're gonna think about our unknowns. How much time? Well, we're looking for T. I'm trying to get my mouse moving here. We're looking for T equals question mark. And again, because this is a Y component, and we're going to do this as a drop problem, we're going to say that G equals positive 9.8. It's going to start from rest. It's dropped, so that's implied. Again, the mass doesn't matter. The interesting thing about kinematic equations is that mass is not in the equation, which is good. And it falls a distance of 50 meters. So again, I'm looking for what equation relates these things. It looks like equation 2. D equals VIT plus 1/2 AT squared. VI is 0, so that goes out. T looks like it's going to be the square root of 2D all over G. And when you plug in the numbers, I think it comes out to be 3 point something, but it is what it is. It's a number. And again, you would box that, make sure proper units. So again, this is purely in the vertical. And there are more parts of that question. Again, you can try that if you want to. If you found chapter 2 a good review, go ahead and do this. There's another vertical problem. I'm not going to bother doing it, but you can take a look at this at your leisure and try it out. It's all stuff we did in the last chapter. The key thing in here, and I'll go back to full screen now. Hopefully I'll get my face off the screen. The key thing here is that it's all about components. So projectile motion is no different than horizontal and vertical kinematics, except we have to keep the motion, the x and the y, separate. And to do this, we're going to take the classic example is taking a velocity vector and breaking it into x and y components. Now, the first example is really easy because we're already in a, this vector is 10 meters per second in the x direction. Well, the VAX is 10. The VAY is 0. So in this case, this is 0 and this is 10. That didn't require any trig, didn't require any thinking, just looking at it. In this case, same idea. The x component of this vector is going to be 0, and the y component is going to be 10. And it's only when you get a vector, like in case C, where it's moving in both the x and y direction, do we have to break this into x and y components. And we do that with the basic trig. We remember that the x component, and I can't draw, but the x component is going to be, if this is the angle. So here we have the hypotenuse, here we have the adjacent side. If that's the given angle, then we can use cosine for the y component. Again, very poorly drawn because I'm using the mouse. We're going to use the sine function, the trig function sine, because it's the opposite. And again, that's all review for you, hopefully. Let me go back and get my thingamabobber there. Okay, so again, nice review for you. I'll try to go a little faster here. Probably the most important thing to understand with projectile motion is, let me just run this and then stop it and reset it. The most important thing to remember is if I have a velocity vector, or any vector for that matter, and in this case velocity, I'm going to shoot a projectile up through the air. It's going to follow a parabolic path back down. As I run this, I'm going to show you the x and y component as a function of time. And off that goes. The key thing to remember is that because in the x direction, it's Newton's first law, the forces are balanced once it's been shot. Once this thing's in the air and under free fall conditions, the x component stays exactly the same. It doesn't change because the forces are balanced. So no net force, no change in velocity, no acceleration. So the x component the entire time is the exact same magnitude, exact same direction. The y component, however, because it's undergoing an acceleration, in this case, it's under free fall, so it's feeling a downward force due to gravity. Therefore, it's going to be decelerating on the way up. The vector still in the up direction, but the magnitude is reduced. And of course, finally, we get to the top. It goes to 0. As it starts back down, it's going to point in the other direction, and the magnitude will increase. And again, that's why quite often when we do projectile problems, we do the break at the top. Something significant happens at the top. The direction of the velocity vector changes and the velocity reaches 0. So again, that's probably the most important thing to remember about projectiles, and that's what allows us now to go ahead and solve our problems with our familiar grid pattern. And this is, again, this is a massive invention. I'm sure other people do a similar thing, but we think the best way to learn projectiles and to really analyze motion is to break things literally apart. We have the x component, we have the y component, and then the y, because the balls could be going up and down, we break that further into up and down. This avoids the need to use subscripts to death and getting confused about which v is which v. So if you do it in columns, keep everything the x and the x, everything the y and the y, everything the up and the up, and everything the down, you'll organize information well, and I think you guys found that last year. The key thing to remember is the only thing that moves back and forth is going to be time. We only have one object, so although the object's moving up and down and it's moving left and or right, it's only one object. So time is the only variable that moves back and forth across those categories. The other thing to keep in mind is that there's really 3 types of projectiles. There's the type of projectile where the object is moving horizontally and then falls. In that case, all of its velocity vector initially is in the x direction. There is no vi, so the vi y is 0. And we'll take a look at that in class. The other examples are, let me go back and get my pen now. Unfortunately, this is going to be a back and forth thing, but so again, for the first case, I'm going to have a mouse that's out of control, but we're going to have the objects can come off the table, and then because there's no table holding it up, it's going to undergo free fall. So again, the velocity vector is all in the x direction initially, and then it will start to develop a y component. The other type of projectile is when the object starts on the ground, we kick a soccer ball, goes up to the air and comes back. It lands on the exact same elevation. And those problems are pretty easy because they're symmetric. The last type of problem we're going to take a look at, and these again are all the same idea, is that the balls of the object, the projectile, starts at one elevation and ends at a different elevation. And again, my drawings are poor, but these are representing parabolas. So you really have, it's really the same type of problem, but this is, again, starts with an initial velocity of 0. If we drop a package from an airplane, the ball rolls off a table, kick a soccer ball, throw a baseball, and then do something off the top of the building or onto the top of the building, something like that. So those are the 3 general types of problems we have when we're doing projectiles. I want to do one quick sample problem just to model this, and again, just bear with me as I do the drawing. You might want to put this in your notes if you don't remember this from last year too well. So if I go ahead, I'm going to take a look at this and say, well, we got a ball that's going to get kicked with an initial velocity of 25 meters per second. It's at an angle of 37 degrees relative to the horizontal. So the ball is going to get kicked off the ground. It's going to fly through the air and land back on the ground. And again, it should be a parabola. I like to get it approximately right. So this angle is 37 degrees, and the initial velocity here is 25. Again, I'm going to take a look at my x, my y, my up, and my down. Because I know where this is going, I've sort of skewed things, make space. Because this is symmetric, we can either do the up or the down. We really don't have to do both. If you had a problem like the case 3 I just showed, where we took off and landed at a different elevation, we may have to use both these columns, but you may recall this. First of all, I want to find the range. Now remember, range is going to be the distance in the x direction. So I'm looking for dx. And the other thing I'm looking for is total time. And again, if it's total time, I can get the time up or the time down and double it. So a couple of things. Let's start with the x. You may remember, because it's Newton's first law, the acceleration is equal to 0. And because we're looking for range, these problems are all the same. And we're looking for d. And again, because I'm using columns, I don't have to use subscripts. This looks like equation 2, VIT plus 1/2. That was really bad. 1/2 AT squared. Again, because a is 0, that all goes out, and this turns into our familiar velocity as distance over time. I can get my range by knowing the initial velocity in the x direction and my time. Well, my v initial is going to equal the v that was given times cosine theta, because the angle was given between the horizontal and the velocity vector. So I'm just going to plug in my numbers, and so that's going to be 25 cosine 37, and that gives me a number. And I don't know what the number is, nor do I really care, but it's a number. I know it's going to be something less than 25, so it's, I don't know, 17, something like that. If we come over, so I have that, all I have to do now is get my time. And of course, I can't get time in my x component, so I'm going to have to go over to my y to get my time. And again, this is very similar to what you did a couple thousand times last year. When I'm doing the problem as an up, well, again, I have to get my initial velocity. So my initial velocity is going to be my given v, my 37. But now I'm going to be using the sine function, because now I'm looking for the y component of that. This should make sense if you think back to the unit circle that you guys did in pre-calc, I think. So sine theta. And so I go ahead and do that, and it's going to be 25 sine of 37. Just learning how to use this pen, so bear with me. And so my VI in that case will equal something. It's going to be my y component. And again, it's probably less than half, so it's going to be somewhere around 10 or something like that. Again, a number. So I can calculate that. The other thing to remember is, because I'm doing it as an up, I'm going to have my A is going to equal negative 9.8. And my VF is going to equal 0. And so I can get time by using equation 1, rewriting it. Time is VF minus VI all over G, or A. And when I get that, I'll get a time. Well, when I get that time, remember we're in the up column, right here in this up column, it will be the same as the time down. So T up will equal T down. And the important thing is, remember, time is the only thing that can come over. I know that to find the distance, the total distance this thing traveled at a range, that's going to equal VI times T. But be careful, it's going to be total time, because this ball has to go up and down. So I'm going to take the VI, calculate here. I'm going to get the total time by adding these two together and come over, and I'll get my total distance. I'll leave it for you to do the calculation. Again, the number is the least important thing. So in this problem, using this technique of using the grid and refreshing our memory about how to break things into parts, in this symmetric case, I was able to calculate the total displacement, or the range, the distance, and calculate the total time the ball was in the air. So again, quick review about how to do a sample problem. And we'll do a bunch of those in class, so don't worry. Let me get rid of this thing again. Again, the thing I'm most interested in is why. Why did it hit at the same time? When we analyze motion, X and Y, I think you can go back to Newton's laws, and I will do a explanation in class using relative perspective is another way of looking at it. So I'll come back to that in class. The other thing that was kind of interesting is the angles that yield the greatest range. Remember, range is dx. So here's a girl kicking a soccer ball, and if you play sports, you intuitively understand this. You don't pull out your calculator and calculate stuff. You want to throw a ball far or kick something far. It's intuitive. You've practiced this a couple thousand times, but it's asking you what angle from the ground, from the horizontal, with some initial velocity, what angle will yield the largest range? And you guys probably remember that this is going to be 45 degrees. And if you went into a little more depth, you'd actually figure out why, and we may do that if you don't remember. The ball is kicked. The other thing that's interesting, if you kick the ball at 30 degrees and it goes a certain range, what other angle will yield the exact same range? So if I kick it at 30 and it goes 100 meters, what other angle will also have it land at the exact same place? And again, based upon the trig that's involved, most of you probably remember that it's going to be the complementary angle. I think it's complementary. It's going to be 60 degrees, and I'll show you that with a simulation, again, done in interactive physics. So here I have a simulation where I've given the ball some initial speed. Here's the ball right here. I'm going to give it some initial velocity. Here's the initial angle. I'll kick the ball. Boink, lands there. Stop, reset. So that's the maximum range I got. And, so we can see it visually. Now I can change the angle. So and I don't have very good control over this, so bear with me. Ooh, almost got it. If I try to get this down to 30, which will probably take about half an hour. Let's see. Okay, good. There's 30, so I'll hit run. It will now launch at 30, and you can see that the range for 30 is less than the range for 45. Now to see what the complementary angle will be, I'll drag it up to 60, and again, hopefully I can get it there relatively quickly. If not, I'll just try to get close. I can show this in class a little bit better. There we go. So if I hit it at 60, you'll see it'll have a higher flight path, but it should land at the exact same location that we had for the 30. And because the simulation is perfect, boink, hits the exact same location. So again, that's kind of interesting. We can figure that out by looking at some of the trig. And that's, again, what we're really interested in. It's not the answer we care about, but it's the underlying physics that explains that answer, which is the most important thing. So again, I think you learned that last year, but you may not remember why. We will not save that, and I believe that's it. So here's our blank screen. So that was a real quick review of projectile motion, probably what took us several weeks last year, a bunch of labs. We basically burned through chapter 3 in about 10 minutes. So I hope that helped, and we'll talk about it in class. Thanks.